So today I'm starting lecture 71, and today we are going to discuss some of the components which are there in the ACO metaheuristics. And I'm Dr. Ranjan Ganguly. Now we saw that there were three aspects of the ACO metaheuristics. The first one was construct and solutions. Now in this component, M ANDs create solutions which come from a finite set of solution components. So essentially we have these solution components Cij, where I is from 1 to n and j is 1 to di. So these are the discrete possibilities of each of xi. And these solution components are the finite set from which the ANDs must create solution. Now when you start the process, the constructions of the solutions essentially starts from a null set. So this null set at that point is SP equals this null set here. Now at each subsequent construction step, a feasible solution component from the set of feasible solutions is created and put into the set SP. So each of these components is essentially from this set C, so these are all subsets of C. Now the selection of a solution component from NSP is done at each construction step, and this selection rule is probabilistic. Several different rules have been discovered or proposed by different researchers. We are going to follow the rule known as AND system proposed by Dorigo. So this AND system AS rule, that's given in this manner. So essentially what this is telling you is that the probability of selection of a certain value SP is going to be this particular ratio, where again you recall that tau are the pheromone values, and this is the summation of the quantity here. So to look at this construct and solution probability more closely, we see that in each of these cases, tau ij is the pheromone value, and then Cij is the heuristic value associated with the component eta ij. Now let us turn to the second set of tasks, which are the Daemon actions. Now these are some problem specific tasks which are built into the metaheuristic, and these tasks typically cannot be performed by the ANDs separately. For example, we could create local searches which could be used to the constructed solution. So these local searches could enhance the constructed solutions. These would be examples of Daemon actions which essentially run in the background. The pheromone update rules, for example, could be generated using the locally optimized solution. Again, remember that the Daemon action step is an optional step in the ACU, so you can skip this particular step if necessary. You don't have to include Daemon action in the ACO algorithm. The pheromone values associated with good solutions are changed as time goes by. So what happens is that you increase the pheromone values associated with selected set of good solutions SUPD. So these are the values which are good corresponding to that. So they are updated here, and UPD refers to that particular fact. So whenever we are doing evaporation, we are essentially forgetting old solutions and weakening the bad solutions. So these two steps are both captured through that evaporation process. So let us now look at the mathematical formula which we use for this kind of update rule. So this is given by tau ij is equal to 1 minus rho tau ij plus rho sigma of f of s, where f of s is essentially a fitness function. Now, if you look at the two extreme situations here, if tau is 0, then essentially this term involving the fitness function becomes 0, and all you have is tau is equal to tau. So essentially that means there is no particular change in the pheromone. So that is one extreme case. The second extreme case is of course the possibility that rho equals 1, and in this case essentially you carry this fitness function value with you. So depending on the weightage you want to give to the past pheromone values or the current value of the fitness function, you can create some number here, and depending on that we can weigh the past pheromone value or the fitness function value. So when pheromones start vanishing from the path, essentially that is similar to forgetting. And what this helps to do is that it moves the ants toward newer areas of the design space. So essentially what it means is that the ants have traversed this particular path. It's not worked out very well. Maybe it's a long path, and therefore the pheromone has started vanishing. And therefore there is a proclivity of the ant now to go towards the newer part of the design spaces or to investigate the new paths in the TSP problem. Now various algorithms have been proposed by researchers for the rule by which pheromones change with time. We have shown one of those rules here. Many such rules are possible. Now we see that the ACO metaheuristic contains many possible specialized situations which can be used. And we have seen some of the possible formulas which can be used. So today's lecture we discussed about how the probability of selection is calculated and how the pheromone update rule is calculated. These are just two examples of this kind of rule. Now, different rules are of course possible based on research. Again, the Daemon action part is possible because very often many of these heuristic and stochastic algorithms do make use of a kind of local search at different points in the process, because the local search can help you to get nearby minimum points. So very often the heuristic method may take you to a good region, but it may not let you converge at that particular point. So what the Daemon action does is that it helps you to converge to that particular point. Now, one of the first algorithms which was developed for the ACO metaheuristic was the ant system, and that's what we are going to discuss in our next lecture, and that's going to be the final lecture on ant colony optimization. See you then.